So, good morning, students. In the yesterday's class, we have discussed. In the yesterday's class, we have discussed the nuclear physics introduction, the alpha, beta, gamma spectrum, right? And also, we have discussed the Gamma's theory of alpha decay and also neutrino hypothesis. In this class, we are going to discuss the particle physics and the classification of these the elementary particles, and also uh, the conservation laws of these particles. We are going to discuss. Let's see. Uh, Particle physics. We will see the fundamental interactions, classification of elementary particles, and the what is particle physics. So, actually, what is particle physics means? Particle physics is a branch of physics which deals with the constituents of element of matter and radiation. Okay, and also it studies the interaction with them. So, constituents of matter means what? There will be some elementary particles in the nucleus. I mean, in the electrons, protons, and neutrons. We are going to discuss about those elementary particles and also the interactions between them and the other interactions which are occurring in this universe. We are going to discuss about that. Okay, let us see the introduction of these elementary particles. This is the branch of physics which deals with the property, interaction, and structure of elementary particles. We are going to discuss the structure also here. Structure, structure, structure of elementary particles is known as particle physics. Okay, it deals with the property, interaction, structure of elementary particles is known as particle physics. Elementary particles are fundamental constituents of all the matter in the universe. So these are these cannot be subdivided. These elementary particles cannot be subdivided. That's why these are the fundamental constituent of all the matter and radiation. What it may be, the fundamental particles will be the elementary particles. With these elementary particles itself, these matter and all things are developed. Okay, these microscopic scale particles plays an important role in the universe. So elementary particles are the building blocks of this universe. There are more than 100 elementary particles discovered so far. Up to now, there are 100 elementary particles are discovered, and we will see the types of interactions now. Here, types of interactions. So there are four type of interactions will be there. These elementary particles behavior can be understood by these four interactions. So to study the behavior of elementary particles, it is important to study the nature of interaction between the nature of interaction between the nature of interaction between. Okay, there are four types of interaction. First one is gravitational interaction. Second one is electromagnetic interaction. Third one is weak nuclear interaction. And the fourth one is strong nuclear interactions. What are these interactions? How it will be? Let us see. This gravitational interaction. Here, gravitational interaction, it is the weakest interaction acts between all body having mass. So these are the weakest interactions which we see among all of these four interactions actually. These occurs between bodied of masses. Okay, it is described by Newton's law of gravitation. So this was discovered by whom? It was discovered by Newton's law of gravitation. The gravitational force acting between two particles is of masses m1 and m2 is expressed as like this. So here F indicates the force of attraction or repulsion. this gravitational force acting between two particles. Let us say two particles of masses m1 and m2 are the masses. So between these two particles, mass and m1 and m2, there will be a force of attraction or repulsion will be taking place. That force is given by capital G into m1 m2 by r square. Okay, here r will be the distance between these two masses. Okay, r is the distance between center of masses, and capital G is the gravitational constant. Here capital G is what? Capital G is a gravitational constant. The nature of interaction is attractive and is due to inertia of the particles. Okay, here the gravitational interaction will be attractive in nature. Okay, and these are weakest interaction. Okay, these are the weakest interaction, and these are active. These are attractive in nature. It doesn't depend upon the velocity and orientation of the masses. Here, this gravitational interaction doesn't depend on orientation and masses, velocity of those masses. Okay, its range extended to infinity. So these gravitational interactions ranges will be extends to infinity. It is responsible for the motion of planets. So motion of the planets will be responsible by these taken by these gravitational interaction. These are occurring between two bodies, right? The planets, between the planets also, the interaction will be gravitational interaction. It is the weakest of all four fundamental interactions, as I just now said, of the nature. The gravitational attraction is approximately 10 power minus 38 times the strength of the nuclear interaction. So it is this much less, 10 power minus 38 times. It is lesser than the strong nuclear interaction. The strong nuclear interactions means the interactions between, in the earlier class, I have said that the strong nuclear interactions occurs between the protons and neutrons, isn't it? Protons or neutrons, those are hold together because of the strong interaction, nuclear interactions. So this gravitational attraction is 10 to the power of minus 38 times lesser than this strong nuclear interactions. So if you go further, next one is electromagnetic interactions. We have gravitational interaction, electromagnetic interaction, weak interaction, and strong interaction, isn't it? So the second one is electromagnetic interaction. How it occurs, where it occurs, let us see. So it is a charge dependent interaction, hence it operates on charged particles. So if you take any masses, let us say, if any two rocks, it doesn't have charge. If those don't have the charge, then there cannot be interacted by electromagnetic. Did you understood? So any particles which are having charges, those can only operate these electromagnetic interactions. It is a charge dependent interaction. So these are charge independent and dependent interactions. Hence it operates on charged particles. It provides atomic and nuclear binding forces. So these provide what? These provide atomic and nuclear binding forces. It is of long range interaction and described by Coulomb's inverse square law. So here, these are long range force interactions. Just now we have discussed the gravitational interaction where it is a weakest interaction, and these are long range interaction, but not that much weak here. So these occurs between two charges. We have seen Coulomb's inverse square law, that is, if Q is any charge here, if you consider, so if you consider two charges, let us say, Here this is plus plus charge, that is plus Q if you consider, and okay, if I consider this as plus Q and another charge is minus Q, if the if the distance between these two charges is R, let us say, then the Coulombic attraction or repulsion force is given by what? This is two charges, that is Q1, Q2 by R square. One, there will be one constant, that is K, that is given by 1 by 4 pi epsilon naught. That is the electromagnetic interaction. That is due to the electromagnetic interaction, because these two are having a charge, right? So these two are having charge. That's why that's why these are having electromagnetic interaction. These are long range interactions. So these are described by what? These are described by Coulomb's inverse square law. Okay. Proton acts as field particle of this interaction. So here the proton will be acting as a field particle interaction. The electromagnetic interaction is weaker than the strong interaction. So these are the weakest than strong interaction, but stronger than the weak and gravitational interaction. So here the electromagnetic interactions are weaker than the strong interaction, but thus are stronger than weak and gravitational interactions. Means what? It stands second. After strong interaction, the electromagnetic interactions are the second one, because these strong nuclear forces are the strongest of all four, and the electromagnetic interaction is the it takes the second place. Okay, it is associated with electric and magnetic fields. Here the electromagnetic interactions are associated with electric and magnetic fields, and is responsible for atomic structure, chemical reactions, the attractive and repulsive electromagnetic forces associated with electrically charged particles. Due to these electromagnetic interactions, only the atomic structures will happen, because electrons which are having in the sorry, protons and electrons which are having a repulsive force, Coulomb repulsive force, sorry, Coulombic attractive force, and the forces between the protons and protons also, it will be in a Coulomb repulsive force. When the nucleus is higher, then there these electromagnetic interactions occur, so that the atomic structures and the magnetic field and electric field will be given. Okay, so here we have weak nuclear interactions. So as a next one is weak nuclear interactions. So in the weak nuclear interactions, in the weak nuclear interactions, these type of interactions are described by Fermi in 1938 to explain beta decay. So beta decay and weak decay of elementary particles like pions, k-mesons, and some hyperons. These are the things we will get when the beta emission occurs. As I said in the earlier class, that beta decay will be occurring by changing proton into neutron and the neutron into proton, isn't it? When a proton changes to neutron, there will be stability of that nucleus by changing that proton into neutron, because the interproportionate of protons and neutrons, where there is number of more than where there is number of protons more than number of neutrons, then the proton will convert into neutron, isn't it? The proton will convert into neutron. So when the proton converts into neutron, there will be balance of these protons and neutrons, where the stability of that atom or nucleus will happen. Here, in this case, as that proton changes from proton to neutron, there will be there will be emission of some energy. That energy is given as a pions, k-mesons, and hyperons. So these these will be occurring in this weak decay of beta decay. So uh, these are the elements we'll get actually. So it is very short range force, about 10 to the power of minus 12 meters. So it is what? It is very short range interaction. Okay. Next, we are going to discuss about the last one, that is strong nuclear interactions. We have discussed this in the earlier class, strong nuclear interactions. Let's see. So strong nuclear interactions, it is strongest force in nature. So these are the most strongest force of all the four nuclear interactions. First one is this one, and next one is electromagnetic interaction, and third one is weak interactions, and fourth one is gravitational interactions. These are the this is how they will frame themselves as strongest of all these things. And next, if you see this one, it is the strongest force in nature. It is responsible for holding protons and neutrons together in the nucleus. Without these strong interactions, there will not be any matter in the universe, because as these protons and neutrons get to hold together, we will get a matter, any uh, any object, any molecule will be found by these strong nuclear interactions itself. So it is the strongest force in nature. It is responsible for holding protons and neutrons together in the nucleus. Hence, it occurs between two protons or two neutrons, or between proton and neutron. It may occur between two protons or two neutrons, or proton and neutron. Because neutron is neutrally charged, proton is positively charged, there may be strong interaction between these two also. It is a short range force when these two protons are very near to each other, very near in the Fermi level. These these positive charges also attract with each other, and they get to hold, and they will dominate the Coulombic repulsive forces of electrons and protons, sorry, protons and protons, and they'll bind together due to these nuclear interactions itself. So these strong nuclear interactions are the cause for the whole universe actually, because these hold together these protons and neutrons and every matter. So it is charge independent interaction. It is what? It is a charge independent interaction, because there are two protons which are two positively charged, but they are having some attraction between them, isn't it? They are charge independent. Even if you take a proton and neutron, one is positive and one is neutral, right? So here the positive is attracted to a neutral one. It is also charge independent. We can say by uh, telling these examples, we can say that strong nuclear interactions are charge independent. Its time of interaction is about 10 to the power of minus 23 seconds. So its time of interaction is how much? Is about 10 to the power of minus 23 seconds. It is very short time, right? So it is short range force, about 10 to the power of minus 14 to 10 to the power of minus 15 meters. Means 1 Fermi, nearly 1 Fermi, means less than 1 Fermi also there. So this is a short range force. It occurs in a short range force. When the distance between these protons and neutrons increases, there will be no strong nuclear forces or nuclear interactions will occur. There will be Coulombic repulsive forces will be occurring between these things. Okay, these are the four nuclear interactions, or fundamental interactions, we will say. The strongest of all is a nuclear interaction, and next is electromagnetic interaction, and third one is weak interaction, and the fourth one is a gravitational interaction. Remember these four interactions, and let us see the next slide. These are the four fundamental interactions of the particle. You just see this one. Here the force is what? Gravity acts between objects with masses. It acts with what? Between what? Between between the two masses. All particle with mass. Particles experiencing is what? All particles with mass. So much force carrier particles. What are the force carrier particles in this gravitational interaction? Gravitons. So these are not yet observed. They are saying that these are not yet observed uh, by experimentally, but these are gravitons. They are saying force carrier particles are gravitational interactions carriers actually. So these are infinite range because here is a Earth. There somewhere is Sun. It is long range, isn't it? So these are relatively strength means it is much weaker of all the three interactions, of all the four interactions. And if you see for weak force governs particle decay. So here weak forces are occurring due to the particle decay. So quarks and leptons are the particles experiencing. So these are the experiencing particles. Quarks and leptons. We will come to know what are quarks and what are leptons in the next coming class. I mean, ongoing class itself. So force carriers are what? These are W plus, W minus, and Z. And short range forces. These are what? Short range forces. Here, gravitational is infinite range, and electromagnetism. Electromagnetism, that is electromagnetic interaction, acts between electrically charged particles because if there is positive charge, if the both particles are positively charged, not a short range in a not short range distances because short range distances means strong forces attracts, isn't it? It is above the Fermi levels, 4 to 5 Fermi level. So there, electromagnetism, electromagnetic interaction occurs. Electrically charged particles are a particle experience, and force carriers are what? Photons. Photons are the force carriers in the electromagnetic interactions. These are also infinite range interactions. Strong forces, if you go for the strong forces, binds quarks together. So these forces will bind the quarks together. What are quarks? We will see. Uh, Quarks and gluons are the particle experiencing in this one, and these are gluons are the force carrier particles in this strong forces. So gluons are what? Gluons are the force carrier particles. Okay, the range will be a short range. This occurs in the short range. If you go for the strength of these all forces, if you see these forces, strong forces are the much higher, stronger than interaction, than weak force interaction and gravitational interaction. So among all four, gravitational is a very weaker than force weak interactions, then electromagnetic interactions, and strong force interactions are the strongest of all. So these are the four fundamental interactions between interactions occurs in the universe. So next we are going to study the particle physics. Just now we have said particle physics deals with what? Constituents of matter and radiation and interaction between them. So these discuss about the elementary particles actually. Constituents of matter means matter consists of protons, neutrons, electrons. I mean, an atom consists of protons, neutrons, electrons. So there will be some constituents in that also. Those are elementary particles, we say. Those elementary particles cannot be subdivided again. Okay. So there will be interactions. These particle physics studies the interactions also. Just now we have studied these interactions between these constant particles, that is nuclear or nuclear interactions, strong force interactions. So let us go for this one. So a branch of physics which deals with the constraints of matter and radiation and interactions with them. So constant constraints means elementary particles here. Uh, Interactions are what? Strong electromagnetic and weak interactions are the interactions here occur. So elementary particles means does that doesn't know that doesn't have any substructure again. Okay. So if you see objects, in the objects we have molecules, isn't it? In the molecules, what we have? In the molecules, we have atoms. In the atoms, each atom consists of means a nucleus. A nucleus consists of protons and neutrons, and electrons revolving around the nucleus. So atom consists electrons, protons, and neutrons, isn't it? So here the protons and neutrons are made by these quarks. Quarks are the cause of the protons and neutrons. Here the are leptons are the cause for these electrons. So by this we can divide these elementary particles as quarks and leptons, and also we can write as a photon, another one, a light photon we can write. So that is also one cause. So here elementary particles are basically they are quarks and leptons. Leptons consist of electrons and its neutrinos and muons. Okay, let's see these. What are these quarks? What are these leptons? And how they behave? Let's see. So these quarks will have spin-off fermions. These will be having spin-off fermions. These are what? Spin-off fermions with a charge plus 2e or 2 by 3e or minus 1 by e. This means what? 2 by 3 is less than charge of the electron. Minus 1 by 3 is also less than charge of the electron. So these are the fermions. Okay, spin-off fermions are called quarks, which are having these charges. So these are not free charges. What? These quarks are not free charges. Free charges have minimum E of charge. So if you see quarks, these are they are saying that these are spin-off fermions, and these are having charges of plus 2e and minus 1 by 3. So if these fermions are having E charge, electron charge, then only they can be called minimum of E charge having particles only called as are the free charges actually. So these are less than this E charge. That's why these are not the free charges. Quarks are not the free charges. So these quarks exist in 6 flavors actually. So these quarks will be existing in 6 flavors. They exist in 6 flavors. First, this is UDCSPB. That is up, up, down, charm, strange, top, bottom. These are the 6 flavors which are observed in the quarks actually. They exist, these quarks exist in these 6 flavors. What are those? Up, down, charm, strange, top, bottom. All the above terms that are up, char, top. These three will be having one charge, and down, strange, bottom. All these three will be having one charge. So the above one, that is up, char, top. These three will be having charge of plus 2 by 3 e. How much charge? Plus 2 by 3 of charge. Here, down, strange, bottom. These three will be having a charge of q is equals to minus 1 by q e. These are the charges of these quarks. Okay, these quarks are existing existing in 6 flavors. Those are these up, down, charm, strange, top, bottom. This up, charm, top are having plus 2 by 3 each charge. Down, strange, bottom will be having minus 1 by 3 each charge. So each quark exists in 3 colors. So each quark of these 6 are existing in 3 colors. Those are color charges. Those are red, green, and blue. What are the colors we are having? Red, green, and blue are the colors you are having. Here, these are the quarks. Actually, we have seen that elementary particles, these elementary particles are basically divided as quarks and leptons, right? So quarks are having 6 flavors. 6 flavors are up, down, charm, strange, top, bottom. And one is the above terms that are up, charm, and strange. Top are having plus 2 by 3 each charge, and below terms three terms we're having minus 1 by 3 charge. Here you have leptons, right? We are going to see what are leptons actually. Leptons are having minus E or zero charge. These are having minus E or zero charge. And fermions, these are what? Spin-off fermions. These are also exist in six flavors. First one is electron and its neutrino. We will call it as neutrino. Electron and its neutrino, muon and its neutrino, tau and its neutrino. These are the six flavors. Here the quarks are having six flavors and leptons are also having six flavors. These are also spin-off fermions. These are also spin-off fermions. Here the charge is plus 2 by 3e and here the charge is minus 1 by 3. Here the charge is minus e and 0. Okay. So these exist in electron and its neutrino, muon and its neutrino, tau and its neutrino. So the above electron, muon and tau will be having a charge of minus e, and electron neutrino, muon neutrino and tau neutrino will be having a charge of 0. Remember this, and these leptons do not have any color charge. Here quarks are having color charge. Okay. So basically elementary particles are primarily they are divided as quarks and leptons. Leptons are having electron and its neutrino, muon and its neutrino, tau and its neutrino. But here the quarks are up down, charm string and top bottom. Let us see these quarks, what are quarks and sorry, how these are quarks are divided again or made up of other terms again. Let us see. So here, the elementary particles, leptons and quarks, right? These are just now we have seen. These are the leptons are free particles. Remember, leptons are free particles because E charge is there. E charge is there. That's why they are free particles. Here, there is less than, there is not E charge. So these are not free particles. These are free leptons. Leptons are, there are free leptons, but there are not free quarks. There will be only free leptons. There are no free quarks here. Let's see the leptons. If you see the leptons example, electron, electron. Why these are free and why these are not free particles? Let us see. Electrons, if you see, if these are two electrons which are having force of which are separated by a distance, let us say r, these are having a force of attraction or repulsion. Let us say these are having some repulsion because they are same charge. So the potential between these two is given by k E1 E2 by r, isn't it? So k is any constant, E square by r is a potential we have. As the distance between these two charges increases, if these two electrons are separated by a distance 2 meters, then the potential will be different, where means potential will be higher. As the distance increase to 4 or 6 meters, the potential will be decreased. Okay. As the r increases, as the separation between the charges increases, the potential decreases in the leptons. So easily they can be separated. They can be easily separated. But in the quarks, if you see, this is one Q1 and this is Q2. They are separated by distance. Again, R, the potential is given between these two charges is minus A by R plus B by R. So this is the potential they are having. If you increase R here, if you increase R value, the VRF also increases. So potential is increasing as the distance between these two charges increasing. Are you getting? In the leptons, where the potential is decreasing when the charge separation is increasing, sorry. So here, when the quarks are separated by some distance, and these are having some potential. If the separation between those charges are increased, then the potential also increases. So it is directly proportional. As we try to separate the V of R is increasing. So if you try to separate this Q1 and Q2, the V of R is also increasing here. So it is cannot be separated. So they cannot be separated, and these are not free particles. These are the leptons of the free particles. Hence, there are no free quarks. So these are the two quarks, Q1, Q2. When they are when we try to separate the quarks, they are not getting separated, and they are attracting. They are having much more potential as they go far from themselves. Hence, there are no free quarks here. So not available as free particles. So these quarks are not available as free particles. Quarks are available as group. So quarks are how they are available. These quarks are available. These quarks are available as groups. Those group are called the hadrons. The group of quarks are called hadron. What the group of quarks are called? The group of quarks are called hadrons. Hadrons. H-A-D-R-O-N-S. Hadrons. These are the bound particles. Whereas leptons are free particles. Here the quarks are bound particles. Okay. Next, if you see, if you again try to classify these elementary particles. These are leptons, these are quarks, right? So group of quarks are called what? Hadrons. So we can write here leptons and hadrons. Are you getting? So group of quarks. Quarks exist as group. So these quarks are nothing but hadrons. We can write the quarks as hadrons. Let us see. So this is how we can write. This is the elementary particles. These are the leptons. These are the hadrons. Hadrons are group of quarks. So these occur as two quarks or three quarks. Okay. So two quarks, 2q are the mesons and 3q are the baryons. Please remember that hadrons are what? A group of quarks. Okay. Quarks occurs only there are bound particles. They are bounded to each other. Whereas the electrons or leptons will be free particle. They are free particle and they can be easily separated. Here the hadrons are group of quarks. As they are separated, they are getting again much more strength of or potential between them. Here the hadrons are 2q and 3q. They are subdivided again. The 2q are called mesons and 3 quarks are called baryons. Okay. So hadrons subdivided as mesons and baryons. So what are mesons? Baryons. Let's see. What are baryons? We will see here. So first, first we see the hadrons. Hadrons are what? Hadrons are the group of quarks. Okay. These are what? Group of quarks. One is plus 2q, that is 2 quarks and 3 quarks. So these 2q is nothing but quark and its uh, complementary. That is q and its complementary, that is qj bar. Okay. These are having the sign spin half and spin half. And this will be the spin of these 2q will be 0. Okay? Plus half and minus half, that is 0 you will get. So here the spin of the mesons is what? 0. The spin of the mesons will be 0. Whereas for 3q, you have 3 quarks here. Spin of each quark is half and they are added. If you try to find the spin of whole quarks 3q, the spin will be plus half and 3/2. These are the two spins will be available for the 3q. That is hadrons, 3q baryons, we will say. These are the mesons and these are the baryons. So two spins will be available for the baryons. So that according to these, by these spins, they are subdivided again. Baryons are subdivided as spin half baryons and spin 3/2 baryons. Are you getting? So here group of quarks are called hadrons. These will be divided as 2q and 3q and nothing but mesons and baryons. Mesons are having spin 0, but baryons are having spin half and 3/2. So that these are subdivided again as spin half baryons and spin 3/2 baryons. Remember this one. So what is mesons? What are mesons then? Mesons are having spin 0. These are spin half fermions actually. So sorry, spin 0. These are called bosons. These are the fermions. These are the bosons. These are what? Bosons. Mesons are bosons, and they are given by pi plus, pi naught, pi minus. These mesons are nothing but these are the elementary particles with the mesons. Those are pi plus, pi naught, pi minus, and k plus, k naught, or k minus, k naught are the and also this is neta naught, neta naught. These are all bosons or mesons. We will say pi plus, pi naught, pi minus, k plus, k naught, or k minus, k naught bar, and neta naught. These are having octet because eight elementary particles are there. Pi plus, pi naught, pi minus are the three. K plus, k naught, and k minus, k naught bar are the four. Seven. These are three plus four, seven, and this one is eighth one neta naught. So whole sum. These are eight octet. Eight. Okay. So baryons are spin off and spin 3 by 2 baryons. What are baryons? Let's see. So mesons are what? Spin 0, which are having 8 elementary particles, that is pi group, k group, and neta group. Okay, let's see the baryons. So here the baryons, if you see, as I just now said, elementary particles are divided as leptons and hadrons. Hadrons are divided as this. Hadrons are nothing but group of quarks. Hadrons are nothing. Hadrons are subdivided again as mesons and baryons. These mesons are having pi group, k group, and meta group. Here baryons. If you go for the baryons, these are again subdivided for spin half and spin 3 by 2, right? So these baryons are subdivided by spin half baryons and spin 3 by 2 baryons. So let us see spin half baryons. Here the spin half baryons contains these elementary particles. Spin half baryons contains these elementary particles. Here these are the elementary particles it will be containing. Suppose spin of baryons. Here a proton, a neutron, lambda naught, sigma plus, sigma naught, sigma minus, cascade naught, cascade minus. These are what? These are the spin half baryons. These are what? Spin half baryons. Whereas spin 3 by 2 baryons are also there. Those are delta plus plus, delta plus, delta naught, delta minus. These are what? Spin 3 by 2 baryons. And this is sigma star plus, sigma star naught, sigma naught star minus, and cascade star minus, and omega minus. These are spin 3 by 2 baryons. So spin half baryons contains protons, neutrons, lambda naught, cascade group, and also sigma group. Here spin 3 by 2 group also contains a delta group. You are getting a delta group, a sigma group again, cascade group, and omega. Okay, these are having here the elementary particles, the elements in the spin 3 by 2 baryons. Those are 10. That's why we'll call it as a decuplet. And here we are having in the spin of baryons, we are having 8 elements, that is cascade 2, sigma 3, proton, neutron, and lambda. We are having 8. That's why we will call it as octet. In the mesons also we have 8 elements. We will call it as an octet only. Here the spin 3 by 2 also having, spin half also having 8 elements, that are octet. Please try to remember these spin half baryons and spin 3 by 2 baryons and mesons. So that you can easily classify all the elementary particles. If you summarize again, what are elementary particles? Elementary particles are leptons and quarks actually. Group of quarks are called hadrons. So leptons and hadrons. Leptons are electron and its neutrino, nu and neutrino, tau and its neutrino. Those are leptons. Hadrons, if you see, hadrons are again subdivided as mesons and baryons. And mesons are what? Mesons are pi group, pi group, k group, and neta group. Here mesons are pi group, k group, and neta group. Here the baryons are again subdivided as spin half baryons and spin 3 by 2 baryons. Spin half baryons means these are having proton, neutrons, lambda, sigma group, and cascade group. They are octet. Pin 3 by 2 are delta plus plus, delta plus, delta naught, delta minus, uh, sigma star naught, sigma star minus, cascade naught star, cascade minus star, and omega. These are the decuplet which are having 10 elements in this pin 3 by 2 variables. Okay. Next, go for the next. We will see the classification by each term. We will try to learn each term of this classifications here. Let us see. Theoretically, we will see what are these elementary particles. So, as I just now said, these elementary particles, these elementary particles are classified on the basis of their nature and properties. They are classified on the basis of mass, charge, average lifetime, spin, interaction, etc. So, the elementary particles mainly classified into three categories. So, what are those categories? Let's see. So, just now I have said leptons, hadrons, I have said. Photons also I have said, but I have not included in the earlier slide. But photons also there. They are divided as elementary particles are divided as leptons, photons, leptons, and hadrons. These names are taken from Greek. So these elementary particle names, photons, leptons, and neutrons, hadrons are taken from the Greek. Okay. In Greek, hadrons means bulky. So hadrons are nothing but in the Greek terms, these are called bulky. That's why group of quarks, we will say. Leptons means light in weight. So leptons means what? Light in weight. And lightweight particles will be having more lifetime than the bulk materials or masses. Okay. So this is the classification according to this one. Photons, leptons, and hadrons are classified from these elementary particles, and the hadrons are what? Bulky in nature, leptons are lightweight, and photons are photon. Let us see. Next slide. If you go for the next slide, what are photons? If you see, so photons represents quantum of radiation having energy. E is equals to h nu, where h is the Planck's constant and nu is the frequency. As we know, uh, these photons are what? This represents the radiation. Okay, this represents radiation of energy, and that energy E is given by h and nu. H is the Planck's constant, nu is the frequency here. So they travels. These photons will travel with the velocity of light. They will travel with the velocity of light. They are they have stable, neutral, and zero rest mass. These are having stable, neutral, and zero rest mass. These are having stable, neutral, and zero rest mass. These doesn't have any. So they are stable again and also neutral. They won't participate in interactions. Okay, here they have spin equal to 1. These are not half spin integral. The spin is equal to 1 here. They obey Bose-Einstein statistics, hence they are called bosons. These photons are called bosons. Photons can be created and destroyed. These can be created and also destroyed. Can destroy these things. It is the force carrier for electromagnetic interactions. So for the electromagnetic interactions, these are only the carriers. Photons are the carriers, so that the light is nothing but a photon. So that carries the electromagnetic forces here. So or these are responsible for the electromagnetic interactions here. Okay, let's go for the leptons. Leptons means light in weight. They are what? Light in weight. They obey Fermi-Dirac statistics. They obey what? Fermi-Dirac statistics. Hence, they are called fermions. Hence, they are called fermions. The photons are what? Those are Bose-Einstein statistics. They obey Bose-Einstein statistics. But here, The fermions, the leptons obey uh, Fermi-Dirac statistics. That's why they are called as fermions. So leptons are fermions. They have spin equal to half. They are having spin equal to half, whereas photons are having spin 1. Okay, there are 6 leptons in total. So these are having the leptons are having 6 spin. Three charged leptons are called the three charged leptons are called the three charged leptons are called electron-like leptons, while the three neutral leptons are called neutrinos. Namely, have said these things. These are two here. Three electrons are called three neutral electrons are called neutrinos. These are neutrally charged. Okay, I have said electron and its neutrino. Electron neutrino, muon neutrino, tons, and tau neutrinos. These are the 6 particles I have explained just in the before slides. I have said electron and its neutrino, muon and its neutrino, tau and its neutrino. These are classification of the electrons. These are the elementary particles of electrons. Next, if you go, if you go for uh, about these electrons, muons and tauons, let's see. Electron is the first elementary particle discovered by J.J. Thomson. This is the first elementary particle discovered by J.J. Thomson. They have negative charge. They have stable and spin equal half. So these electrons will be having spin half. The mass of the electron will be 9 into 10 power minus 31 kg. Okay, it has charge of equals to minus 1.6 into 10 power 6 16 coulombs. Muons are the first discovered cosmic rays. Muons are what? First discovered cosmic rays. They have charge -1. So they have spin equal to half. These are all electrons will be having spin half. So they are the muon is unstable subatomic particle with mean lifetime of 2.2 microseconds. The muons will be having 2.2 microseconds of lifetime. Muons have mass about 10, no, 207 times that of the electron. So the electron's mass is much more less than this muon mass. Muon mass will be more than the electron. Tons next have recently discovered. These are the recently discovered particles. It's similar to the electron with negative charge, sorry, negative electric charge and spin of tau leptons have lifetime of lifetime of 2.9 to 10 power minus 13 second. Okay, they are having a lifetime of 2.9 into 10 power minus 13 seconds. So to go for next, all the three neutrons, electron and its neutrino, and tauon and its neutrino, muon and its neutrino, all these three neutrinos which are having neutrally charged, they are stable. Neutrinos are stable, no charge, and spin is equal to half. Each neutrino has corresponding antiparticle. Antiparticle means it has anti-neutrino. Okay, neutrinos can be created in several ways, including in certain types of radioactive decay. We have seen the beta decay, right? Neutrinos are created in the beta decay. In the yesterday's class, we have discussed about this beta decay neutrino things. So those are about the leptons. Leptons, we have discussed about electrons. Now we are going to discuss the hadrons. Hadrons classification. Here hadrons are defined as strongly interacting composite particles. Hadrons are further classified as mesons and baryons. So hadrons are what? Strongly interacting ones. And these are classified as bosons and mesons. Mesons means medium in mass. So mesons will be having medium in mass. Mesons are unstable subatomic particles composed of one quark and one antiquark with longest lived lasting for only a few hundreds of the microseconds. So these mesons are unstable subatomic particles. So this contains one quark and one antiquark. As I just now said, two q bar I have said, right? One is quark and one is antiquark with the longest lived lasting for few hundreds of a microsecond. That much life will be visible. So mesons mesons will be having pions, pions, and that is neta meson. So pions means pi plus pi minus and pi naught. Pions means k plus k minus and k naught. And these are the neta mesons. Next, we are going to discuss the baryons. Baryons again, we have seen that they are subdivided as two, right? And also we have to discuss about the pions and also cons and these subdivisions also we are going to see. So here the pions, if see pi mesons, these pions have three subatomic particles, pi naught, pi plus, pi minus. Each pion consists of quark and antiquark. Each will be consisting of quarks and antiquarks. Pions are the lightest mesons because they are composed of lightest quarks. They are unstable with the charge pi plus and pi minus decaying with a mean lifetime of 26 nanoseconds. This lifetime is uh, 26 nanoseconds, that is 2.6 into 10 power minus 8 seconds. The neutral pi naught decaying with a shorter lifetime, much shorter lifetime than this pi minus. So that is 8.4 into 10 power minus uh, 17 seconds. Charged pions most often decaying into muons and muon neutrinos, while neutral pions generally decay into gamma. So these are generally neutral pions are generally decaying to gamma particles. Okay. Next, kaons, K mesons, we will say. These are the kaons. Kaons are K mesons. They exist in three states. That is K plus, K minus, K naught. Okay. They discovered in cosmic rays in 1947. These are discovered in the cosmic rays in 1947. They are unstable. Their mean life is about 10 power minus 8 seconds. Okay. That is neta mesons. Again, they have no charge, heavier than the mesons and unstable. Their mean lifetime is 10 power minus 18 seconds. That is very much less than the K mesons. Okay. So next we are going to discover about baryons. Baryons again subdivided as spin-half baryons and spin 3 by 2 baryons. I have said, right? So the baryons means what? Heavy. Heavy particles are the baryon particles. So that they are called as baryons because of this mass. So here a baryon is a composite subatomic particle made up of three quarks. So baryons is made up of three quarks, whereas mesons are made up of only two quarks. One is quark and one is anti-quark, right? That's why they are uh, zero spin. Baryons belongs to hadron family of particles. They are the parent of these baryons are hadrons, right? So hadron family of particles it belongs to. They have spin off. They include nucleons, hyperons, and resonances. These are the three included in the baryons. Let us see about these three inclusions. That is, nucleons. First, you see, nucleon is one of the particle that makes up the atomic nucleus. Each atomic nucleus consists of one or more nucleons. So, nucleon is one of the particles that makes up the atomic nucleus. Atomic nucleus is made up of nucleon. Okay? Each atomic nucleus consists of one or more nucleons. Okay, and each atom in turn consists of a cluster of nucleons surrounded by one or more electrons. Okay, they are spin There are two known kinds of nucleons. Those are protons and neutrons. Neutrons and protons are the nucleons. So neutron, what is neutron? Neutron is a subatomic particle which is given by the symbol N with no charge, with no electric charge and mass slightly larger than the proton. The proton mass is somewhat less than this neutron. Okay, the number of neutrons in the nucleus equals to mass number by atomic number. Atomic number is nothing but number of protons. Mass number is nothing but mass of the nucleons, that is protons plus neutrons minus again protons, you will get the number of neutrons. Okay. Next one is number protons. If you see proton is subatomic particle that is just like a neutron. So symbol is P here with a positive electric charge. Whereas the neutron is neutrally charged, here the proton is positively charged of +1 elementary charge and mass slightly less than that of the neutron. The mass of proton in atomic nucleus are equal to the atomic number of that. So atomic number is nothing but the number of protons. Okay. Hyperons. Let us see hyperons. What are hyperons? They are unstable and spin equal to half. They are unstable. These hyperons are very unstable and the spin is equals to half. They are discovered in cosmic rays. They are discovered in where? Cosmic rays. They are fermions. Their rest mass is greater than nucleons. Their rest mass will be greater than nucleons. So these hyperons includes what? These hyperons include sigma plus, sigma minus, sigma naught, omega, cascade minus and cascade naught, and lambda. These are the hyperons, we will call it as. These are unstable and they are having the spin off and they discovered in the cosmic rays. And these are the fermions, okay? Sigma group, omega, cascade group, and lambda. These are the four groups which are called as the hyperons. Remember. So resonances. Resonance particles or resonances is that they are extremely short-lived particles. These are very extremely short-lived particle. That's why their lifetime is order of 10 power minus 23 seconds, traveling at the speed of light. So these particles could only travel about 10 power minus 15 meters or about the diameter of a proton before decaying. So as it rotates at 10 power 15 meters, it will decay. Okay. So that is why we won't go in depth to this resonance. They are not that much. So here there is a classification of all these things. So elementary particles which are divided as photons, leptons, and hadrons. Photons we know these are what? Carriers of these electromagnetic interactions. So leptons are again divided as electron, neutrino, muon, neutrino, tauons, and tauon neutrinos. These are the six of leptons. Hadrons, group of quarks are called hadrons. This is HA1, hadrons. So hadrons are subdivided as baryons and mesons. Mesons are spin 0 and baryons are spin 3 by 2, spin half and 3 by 2, right? So again mesons are divided as 6, again pi plus, pi minus, pi mesons and pi plus, pi minus, pi naught are the 3 mesons of pi and nu eta is 1 and k will be having k plus, k naught or k naught, k minus. These are octet in nature. Whereas baryons will be having spin half baryons and spin 3 by 2 baryons. Here they have included nucleons. Nucleons means protons and neutrons. Hyperons, which are having sigma group, omega group, cascade group, and lambda group. These are the resonance which are having so very much very less lifetime. Okay. So next you go for this one. If you see the classification again with the symbols, if you see, you can understand easily as like this: elementary particles, leptons, hadrons. These are the field quanta. So here, these are leptons are electron and its neutrino, muon and its neutrino, tau and its neutrino. Mesons are pi group, that is pi plus, pi naught, pi minus, k plus, k naught, k, k minus, k naught bar, neta naught. Baryons are spin half, spin 3 by 2. Spin half baryons are proton, neutron, lambda naught, cascade, sorry, sigma group, sigma plus, sigma naught, sigma star, sigma minus, cascade naught, cascade minus. And the spin 3 by 2 are uh, delta plus plus, delta plus, delta naught, delta minus, uh, sigma star plus, sigma star naught, sigma star minus, cascade naught star, cascade minus star, and omega minus. These are the baryons, right? So these field quanta photons are because in the strong interactions, the gluons are the field quanta here. These are gauge bosons. In electromagnetic interaction, photons are the carriers. In the weak interactions, these are the carriers. In gravity, gravitons are the carriers here. Okay. Next, we will see the conservation laws here. So, conservation of these elementary particles, if you see, that is done as a conservation of charge, conservation of lepton number, conservation of baryon number. So, conservation of lepton number means it occurs in the weak interactions. Baryon number will be in occurring all interactions. Conservation of on isospin will be occurring in strong interaction. Conservation of parity will be occurring in strong electromagnetic interactions only. No weak interactions are here. Conservation of component of isospin. The component of isospin are given in strong interaction, electromagnetic interaction. Conservation of hyperchange will be in strong electromagnetic interactions. Let us see these conservation laws, how we will apply the conservation laws to the elementary particles, and how we will try to find the conservation of charges or the charge of the leptons or charge of any baryons or any, if you try to find the elementary particles, any charge or lepton number or baryon number or isospin or parity, you will try to find how you will try to find. Let's see. So conservation laws here, conservation laws of lepton number, baryon number, isospin, third component of isospin, strangeness. These are the five conservation laws here. The lepton number, if you see, as we know, leptons are what? Electrons and its neutrino, muons and its neutrino, tauons and its neutrino, isn't it? So here, for the leptons, the charge will be, for the lepton number, conservation of lepton, for the leptons, it will be given, taken as +1. For the anti-leptons, if I say anti-lepton means you have electron, which is a lepton. Positron is called an anti-lepton. Just remember, an electron is what? A lepton. Then the antiparticle of that electron is what? Positron, isn't it? So the positron will be having a minus charge here. So other than these leptons are having zero charge. We have to apply zero charge so that we will try to find the conservation of these lepton numbers. Let us see here. So here leptons, these are lepton electrons, lepton muons and lepton tauons. The particle is what? Electron and its neutrino here. The antiparticle is E plus, that is positron, and the positron neutrino here, or the anti-neutrino of this electron. We can say anti-neutrino of electron, anti-neutrino of electron. So we are, the leptons are having only electron and its neutrino, right? Those are having plus charge, +1 charge. But these are the antiparticles of these electrons and neutrino. That's why we'll take it as Le is equals to, that is lepton number is equals to -1. Negative sign, no bar. So negative sign when it is having a bar, we'll keep it as a negative signs for the leptons. Whereas coming for the muons, muon and its neutrino are the particles here. The antiparticles of these ones are plus muons and antineutrino of muon. These are antiparticles. Here we have tauons. that is tau and its neutrino plus tau are the antiparticle of this tau and its neutrino, that is anti-neutrino of the tau is but antiparticle. So we will keep it as minus sign, -1 charge, and it is +1 charge. We have examples here. Mu minus, that is muon, gives rise to electron plus and its neutrino, electrons neutrino, and antiparticle of muon neutron. Here muon is zero charge. You have muon zero charge, +1 charge for the electron, charge for the and its neutron, and its zero charge for the muon also, antiparticle of muon. For Le, that is for the electron only. Charge electron number for the electron. This is electron number for the muon. Only muon terms you have to take here. Muon is there. That's why we will take +1 because it is minus. So that is, it is a particle. Here it is a particle, but it is electron. We will take it as 0. Here the neutrino of that electron, that is also 0. Here the anti-neutrino of muon, that's why we will take it as -1. So these are, in these two, the electron number is not conserved, and also here the muon's electron number is also not conserved. This is how you will find. And if you go for the other example, here the proton gives rise to pi naught plus electron plus positron. If you go for the electron conservation, here it is 0. It is not electron, it is proton. Right? So pi naught is also 0. Electron is +1 and its neutrino is -1. Here it is -1 +1, it will become 0. So electron number is conserved. Electron number is conserved, we can say. Okay. This is how we will find the electron number. If you go for the baryon number, that is capital B. Next one, baryon number. As you know, baryons are again two types, right? Spin off, pin 3/2. So when there are baryons, we will take it as +1 charge. When they are anti-baryons, we will take it as -1 charge. And for the others, we will take it as 0. Okay. Anti-baryons are having a bar. Anti-baryons will be having a bar on the head. Okay. This spin-off baryons, if you see, what are the spin-off baryons? Protons, neutrons, lambda naught, sigma plus, sigma naught, and sigma minus. These are what? These are the, and cascade naught, cascade minus. These are the spin-off baryons. Spin 3/2 baryons are delta plus, delta naught, delta minus. Sigma stars plus, sigma star naught, sigma star minus are the sigma group. Cascade minus, cascade naught star, cascade minus are the cascade group, and omega minus is the, these are the decuplicate 10 elementary particles which are spin 3/2. Okay. Next, we will see the example of the baryon number. How we will find the baryon number for the protons ones, mesons ones, lambdas ones, sigma group, and cascade group. Then we will try to find the lepton number, baryon number after the each of these findings. Okay, let us see. So here, if you see, neutron is a baryon, proton is a baryon, but electron is not a baryon, and its neutrino is not a baryon. So this, here it is one charge. So it is a conserved. Baryon number is conserved. If you go for here, proton is baryon, K plus is not a baryon, sigma plus is a baryon, and cascade minus is a baryon. So here 2, here 2, it is conserved. Here if you see, sigma minus, phi minus, and P. Here sigma minus is baryon, phi minus is not baryon, proton is a baryon. That's why energy baryon number is conserved. This is how we'll find the baryon number. You can see the examples over here. If you go for isospin, isospin only exists for hadrons. So hadrons are nothing but what? Hadrons are mesons and baryons. So isospin doesn't occur for the leptons. Leptons doesn't have the isospin. So let us see for the isospin of the baryons and mesons. Multiplicity. So here, number of particles in a group. So number of particles in a group, how we will find the isospin means we will take the number of particles in a group, that is m is equals to I plus 1. So if you want to find I, we'll take out this 1 to the other side and by 2 also other side, that is m minus 1 by 2. This is the formula. By this formula you can find the isospin of any particles, that is hadrons or mesons. If you go for the proton neutron one, proton neutron group, isospin will be same for the whole group, that is proton neutron group, cascade group, and sigma group. The isospin will be similar for the all the group elements. Okay, so here the proton group is there. So m is 2 is equals to 2I plus 1, right? I is equals to, if you substitute, m minus 1 by 2. So m is number of particles in the group, 2 minus 1 by 2, that is 1 by 2. Isospin of this proton neutron is 1 by 2. If you go for the particles in a group have isospin, uh, isospin depends on number of particles only. So isospin depends on the number of particles. Here if you see, sigma group have three particles. So three particles means 3 minus 1 by 2, that is 2 by 2, that is 1. Isospin will be 1 for sigma group. For cascade group, how you will find? Cascade means you are having two terms only, that is two particles, 2 minus 1 by 2, that is 1 by 2. The cascade group is having isospin of 1 by 2. For you, if you go for, that is lambda naught. Lambda naught, you are only having one particle, that is m minus 1 by 2, that is 1 minus 1 by 2, that is 0, isn't it? The isospin of the lambda will be 0. And also for delta group, you are having four elements, right? 4 minus 1 by 2, you have to find 3 by 2 is the isospin. Okay? 3 by 2 is the isospin. The third component of isospin, that is Iz or I3, we will say. We will try to find the Iz or I3 here. The spin, how you'll find the spin? Ms is equals to minus s to plus s. That is minus, if the spin is half, that is, we'll take minus 1 by 2 to plus 1 by 2. That's like that. Okay. So spin is half. Ms is equals to minus 1 by 2 to plus 1 by 2. Here s is equals to 1. If s is equals to 1, ms is equals to minus 1, 0, 1. We'll take it as like that. Isospin, how you'll find the isospin? As I just now said, if you have number of particles, then by that you can find the isospin. But third component of isospin is nothing but from plus I to minus I. The values of I will be ranging. The I3 will be ranging from plus I to minus I. That is 2I plus 1 values will be there for third component of isospin. Here, if you take the example, I is equals to 1 by 2. If I is equals to 1 by 2, then I3 will be from minus 1 by 2 plus 1. I3 will be minus 1 by 2 to plus 1 by 2. For I is equals to 1, if you go for, that will be I3 is equals to minus 1, 0, 1. Is that the three isospins here? They are possible. So I3 can be found by change of the particle to the charge of the particle to the minus average charge of the particle. Let us see the examples. If you go for the proton charge, proton will be 1 by 2. That is I3 can be found. That is charge is plus 1 and it is minus of. Average charge of the group is 1 by 2. Average charge is 1 by 2 and the charge of the proton is 1. 1 minus 1 by 2, it is minus 1 by 2. If you go for neutron, the charge is 0, but the overall charge, average charge is 1 by 2. 0 minus 1 by 2, that is minus 1 by 2. And for the lambda naught, the charge is 0 actually. I3 is 0 and I is 0. When I is 0, the I3 is also 0 because I3 changes from minus I to plus I, right? So that is how. If you go for other examples of this I3, you can see the other examples also. Here you are having, that is pi group. For pi group, the average charge is plus 1. That is I is plus 1. So for plus pi, that is I minus 0. Plus 1 is the I3 here. For pi naught, the charge is 0. So 0 minus 0, it is 0. For pi minus, it is minus 1 minus 0. That is minus 1. Higher the charge, higher the I3 value. So as the charge is higher, the I3 value is higher. For delta plus plus, it is having 3 by 2 charge. For delta minus, it is minus 3 by 2. Remember that. So these are the mesons and spin-off baryons and spin 3 by 2 baryons and their isospin and the third component of isospins. Okay, we'll try to check these. We will check these isospins, all these uh, charge, lepton number, baron number, isospin, and third component of isospins in these problems. Changes quantum number. What is changes quantum number? Let us see. Indicates the strange behavior of the particles. So changes quantum numbers. S indicates the strange behavior of the particles. This is EP. Elementary particles are divided as electrons and hadrons, right? So leptons are weakly interacting and hadrons are strongly interacting. So these there are some hadrons which are k mesons, pi naught, sorry, lambda naught, sigma, cascade, and lambda omega minus formed through strong interactions. So x plus y is equals to s1 plus s2 formed in the phase of associated production. So but decay through weak interaction. They will decay weak interaction. These are the strange particles. These are what strange particles. We'll try to find the strange particle value by using this formula. Q is equals to I3 plus B plus S by 2. Here Q is the charge, I3 is the isospin, B is the baryon number, S is the spin isospin, that is strangeness, and 2 is the number, it is a 2. Okay, if you substitute these values and you will try to find the S. In any equation, you will try to find the S, they will get the strangeness of that particle. If you go, these are the only groups which are having strangeness, that is k mesons, pi naught, sorry, lambda naught, sigma, cascade, and omega. These are all the groups which are having strangeness. Okay, these are the strangeness factor. Strangeness will be having for k mesons, it will be +1. For anti mesons, it is -1. For uh, lambda naught, it is -1. Sigma group, it is -1. Cascade group, it is -2, and omega group, it is -3. Remember, omega you will be having more strangeness. Strangeness will be much higher than all the terms, all the groups. Strangeness of omega minus is 3. Okay, remember -3. So here we will charge parity and time. If you try to find the charge parity of the and time, the strong interaction charge will be conserved, parity will be conserved, time will be conserved, three will be conserved in the strong interactions. And in my interactions, charge for parity, time, and CPT are the conserved. Weak interactions, no CPT, C charge parity and time conserved, but CPT is conserved. CPT is equals to 1. That is interactions. So leptons, neutrons, hyperons have even rarity. So leptons, neutrons, and hyperons will be having. Hyperons are nothing but lambda naught, omega, cascade, omega minus sigma. Okay, these are even parity. So mesons have odd parity, bosons and antibosons have some parity, same parity, but fermions and antifermions have opposite parity. Linear momentum is found uh, by these these charges of these electrons. The angular momentum also. So how you will find this, whether some interaction is weak interaction, strong interaction, or electromagnetic interaction between these elementary particles. As we have said, electromagnetic interaction is much more stronger than weak interaction than the sorry. All all the hadrons are strong interaction. Percent the strong interaction, associative production. There will be associative production and there will be no leptons in the strong interactions. Leptons, we don't find leptons in the strong interaction. The electromagnetic interaction, you will be getting photon or photon and its antiparticle. Particle and its antiparticle will be present in the electromagnetic interaction equations. Okay, weak interactions you have electron present and strange particle decay. That is, strange particle decay will be there in the weak interactions. This is about elementary particles. fundamental, sorry, fundamental interactions and conservation laws of these fundamental, interactions, elementary particles, conservation laws of elementary particles. Just as we have said, the elementary particles are the constituents of radiations and matters. So matter consists of molecules, molecules consist of atoms, atom consists of electrons and protons and neutrons, protons and neutrons are formed by the quarks, and electrons are the leptons. So they are subdivided as leptons and quarks. Group of quarks are called hadrons. Hadrons are what? Group of quarks are called hadrons. Hadrons are mesons and baryons. And baryons again subdivided as spin-half baryons and spin 3 by 2 baryons. But the mesons are having spin 0. That's why they are divided, uh, classified from the hadrons. So mesons contains pi group, k group, and meta group. Baryons contains spin-half and spin 3 by 2, and spin-half have a state in nature that are 8 elements will be present. Spin 3 by 2 will be having decuplet, that is 10 elements, elementary particles will be there. Okay. So leptons are electrons, muons, and tauons, and these field contact, these interactions will be strong. Interactions will be strong nuclear interactions between the atom, in the atom, that is between neutrons, and these are charge independent. Whereas electromagnetic interactions are between the charged particles; these are charge dependent, and weak interactions are weak interactions are gravitational interactions are between two masses, are between two masses, and weak nuclear interactions are between occurred due to the beta decay. Beta decay. Those will be pions, k-mesons, and hyperons. The, the interaction between pions, k-mesons, and hyperons. This is about the today's lecture. Thank you. The next class we are going to discuss other units. I hope you understood the class. So go through these uh, topics which I have discussed in the yesterday's and today's class. Okay. Thank you. Thank you for participating.